Hey, what up, guys? This is a cute little trig problem. I don't think I've ever done a video just like this, but I felt like I should because it was a problem that intrigued me when I ended up seeing it. So I'm a math nerd, and sometimes I literally just watch math YouTube videos because I like learning more math. And on this particular day, I was watching a video by Mr. Michael Penn, or Dr. Michael Penn. He is a mathematician who does cute little videos. And this one here is his video. So he has this thing called Denny's magical integral, and he does all this calculus work, and he ends up going crazy with it. I'm sure that people who are not in calculus won't know what's going on, but the point is that he had this t equals tangent of x over 2 circled in green on the right hand side of the board. He did a derivative of it, that's fine, but he said with some obvious trig, the cosine of x is 1 minus t squared over 1 plus t squared, and I was kind of dumbfounded, flabbergasted. I was like, no way that is actually true. And he was like, it's obvious. All right, well, okay, maybe it's obvious to some mathematician, but it wasn't obvious to me. So I said, I'm going to go ahead and do it off to the side, and that is exactly what we are doing. We're going to go ahead and show that in the event that t is the tangent of x over 2, the cosine of x must be this whole thing. Let's make it happen. So anytime you're doing a question that is a trig situation, you typically want to pick one equation, work with it the entire way, and get to the other one. We're going to start with this one. The first thing we're going to want to do is we're going to get x by itself and take the cosine. Because if we have x by itself and take the cosine, in theory, the right-hand side is what we want. So let's go ahead and do that. We're going to start by doing the tangent inverse of both sides of the equation. Now, a mathematician might argue that it's supposed to be an arctangent instead of just a tangent inverse. I will not bother making the distinction here because it won't actually matter for this particular problem. So we have tangent inverse of t is equal to x over 2. And again, our goal was to get x by itself and then multiply both sides by 2. Or sorry, get x by itself and then cosine of both sides. So 2 times the tangent inverse of t is equal to x. And now we need to do the cosine of both sides. However, before I do just the cosine of both sides, what I'm going to actually do is move the x to the left so that I can make this problem look a little bit prettier in the future. So we have this x equals this, and now finally cosine of x is equal to, so we were doing the cosine of both sides, we're doing the cosine of this entire thing. Great. Now all we have to do is show that the cosine of 2 times the tangent inverse of t is 1 minus t squared over 1 plus t squared. We're doing awesome. So the reason why we're doing so awesome is that we have the cosine of 2 times something. Now, anytime you have a trigonometric function of 2 times it, there's going to be something nice and neat that we call the double angle identity. So the double angle identity for cosine happens to look like this. We're going to say the cosine of 2 alpha turns out is cosine of alpha, and then we're going to take that and square it, and then we're going to subtract the sine of alpha all squared. You can verify this using a couple different angles on your calculator, or you could see one of those proofs, or maybe I'm going to have to make a separate video to do a proof of what's in this proof. But for this problem, we're just going to assume that this is a true statement for any alpha value. And now, basically, this right here is going to be our alpha. This is going to be our angle alpha, and we're just going to plug it in into this thing. So right away, we can go ahead and say that this right here, the cosine of x, is in fact equal to, and now it's equal to this entire thing on the right-hand side, where our alpha is our tangent inverse of t. So we're going to say the cosine, kind of like started writing below it. Oh well. All right, so we have the cosine of the tangent inverse of t, and then all of that squared minus the sine of the tangent inverse of t. And then we're going to have to do all of that squared. Did I have enough parentheses there? 1, 2, 3. No, I missed a parentheses. This is why I'm not a math professor. What do you know? All right, so we have all that squared. Now, what's going to happen next? So what's going to happen next is we have to do something that is a very common technique in a pre-calculus and above course. Anytime you have a trigonometric function with a trigonometric inverse right next to it, you typically want to draw a triangle where that is a true statement. Basically, what that means is I'm saying that the cosine function always has an input that's an angle. So when I'm drawing this out, we're going to go ahead and say that this right here is in fact an angle that we are going to worry about. So we have the cosine of some angle, and anytime you have a tangent inverse, the inside of a tangent, so I'm going to go further inside now. How about we just use just the letter t here? This right here is a ratio of some kind. That ratio in this particular problem is actually going to be t divided by 1. And because it's tangent, it is going to be the opposites over the adjacents for some triangle. And that's what we're going to do. We're going to go ahead and take our angle, which I'm going to go ahead and say is theta. So we have our theta there, and then the opposite of that theta is t. The adjacent of that is 1, and then t squared plus 1 squared equals the hypotenuse squared, or in other words, the hypotenuse is the square root of t squared plus 1. And now we're doing the cosine of that angle. That's the angle that we just drew. So the cosine of that same exact angle, the cosine of this theta, which again, this right here is theta, the cosine of this one is going to be equal to 1 over, or adjacent over hypotenuse, 1 over t squared plus 1. And if you square that, we're squaring both sides because we're doing the cosine of that entire thing squared. If you take the cosine of theta squared, you end up with that entire thing squared. You get 1 over the square root of t squared plus 1, all of that squared. Well, and 1 squared is 1, and anytime you have a square root in a square, going to be canceling out. Technically, it's absolute value if you're being fancy, but t squared plus 1 can't be negative anyways. So we have our cosine of theta all squared must be equal to 1 over t squared plus 1, and that's looking good because remember our original goal was 1 plus t squared on the bottom. We're doing t squared plus 1. We can rearrange that later. So we're going to go ahead and start writing that in now. We have our cosine of x must be equal to, and it turns out that must be equal to be 1 over t squared plus 1, and I really should have said 1 plus t squared because that's kind of what it was in the video, but that's okay. And now we're subtracting the sine. Now the only difference for sine is exactly the same as all of these, except for these ones are all t's. And therefore, if I was doing it the same exact way, we could say that the sine of theta all squared must be t squared over t squared plus 1. So that's what it is. We're going to go ahead and say it is t squared over t squared plus 1. And sure enough, we have common denominators. We can rewrite that bottom denominator as 1 plus t squared, and we have cosine of x is equal to 1. It's not a 1. 1 minus t squared over 1 plus t squared, w to the 5th, which was what we wanted. We're all done with this one. Beautiful little thing. Have a great rest of your day, guys.